Hi again, I'm Neil. Well, this chapter, it's all about electric potential energy, and this guy, Carl Gauss, a German mathematician of the 18th and 19th century, arguably the single greatest mathematician to have ever lived. His contributions to, well, a variety of things, quite honestly, astronomy, mathematics, physics, and a plethora of other disciplines. Carl Gauss was, simply a brilliant man. And he gave us a way to determine, among many other things, the electric field due to continuous charge distributions using symmetry. And this chapter is going to show us how to do that. Now, if we were to pull up this chapter, the idea is to use the symmetrical nature of a charged object to determine what the electric field is going to be. Now, these are objects with three-dimensional structures to them. For instance, here there's a cube of some length, and there are several different situations going on here. The electric field is due to some charged object that is not in the picture, but the electric field due to that object is, and it encounters a cube of even side. Now, the electric field on one side, it goes into the cube. It may go out of the cube. It may be perpendicular to the cube or parallel to the cube. And depending on the orientation between the electric field vector and what we can define as a surface area vector, that's a vector that's perpendicular to the surface that the electric field is encountering, the product, the dot product of those two vectors gives us a new property of measurement called the electric flux. Now, the electric flux is very useful in integral calculus for determining the electric field that is emanating from an entire object, or an object is being engulfed by an electric field. So, and the reader, as they go through this chapter, will see the different scenarios that are possible with the electric field and the electric flux. Now, one of the more useful things, and this is the equation, this is Gauss's law for electric fields. It's related to epsilon. Epsilon is the permittivity of free space, well, at least epsilon naught is the permittivity of free space. It's a measure of the influence on electric fields going through space or a particular medium. If it's epsilon naught, it says free space. So it's related to the behavior of electric fields. So the permittivity of free space by this new property called electric flux gives us the total charge enclosed by a Gaussian surface. A Gaussian surface is an imaginary surface drawn around symmetrically around a continuous charge distribution. So that's actually quite important. So this imaginary Gaussian surface that's drawn, that mimics the symmetry of a continuously charged object, it gives us a way to calculate, well, several things. Either the total electric field that's emanating from the object or the total charge that's enclosed by the Gaussian surface. So, once the reader has a chance to spend some time looking at the details of this chapter, this will become more evident. And it's useful for many things. Here we show in the diagram at the center that if we had a conductor, a hollow conductor, and we immerse this hollow conductor in an prevailing electric field, the electric field, due to the Coulomb force law, causes a redistribution of the charges, the free electrons on the surface of this conducting sphere to redistribute themselves. And that sets up an electric field within the conductor that opposes the external electric field. When you add those two together, the result is zero. So any hollowed conducting surface in the presence of an electric field has zero net field within the conductor. That's actually a very important conclusion, and it'll become evident why as the reader goes through the details of this conclusion. It has applications in a variety of ways. As we scroll throughout the rest of the chapter, much detail is given as to the generation of electric fields, in particular something called a Van de Graaff generator, which is a hollow conducting sphere, much like we described here theoretically, and here it's shown experimentally. So one of these spheres is conducted, it's a conductor, and it's hollowed, and it's connected to a power supply. And what's not shown, there's a rubber belt that runs through the center of the sphere, and through frictional charging, it charges the outer surface of the conducting sphere such that the electric field, the charges build up so strongly that the electric field has to find a way to ground itself. So if a secondary sphere, this one, is brought close to the conducting sphere over there with the built-up charge, look what happens. There's a spark that jumps. Now we easily are talking about tens of thousands of volts here that builds up. A spark actually breaks down the resistivity of the atmosphere. And the atmosphere, the molecules, they get energized so rapidly that electrons get ripped off and then recombine, and that creates the sparks that's shown in the picture here. So it's the discharging of the sphere due to a high electric field that is building up. So it's a fantastic and very common experimental setup used in labs, all over the place, in all schools. They tend to have a Van de Graaff generator to show the buildup of electric fields. So this is a demonstration of that, and we've created a problem to solve for the total charge that is enclosed, or that is carried by the surface of the Van de Graaff generator. We do an example to show how this works using this imaginary Gaussian surface. So it's quite a useful example. Now we also do several examples of to show the simplicity, the relative simplicity of using Gauss's law to solve for the electric field due to continuous charge distributions that have some kind of symmetry. Now, in the previous chapter, we showed how to meticulously calculate the electric field due to any kind of charge, point charges, discrete charges, or continuous charges. But it was very methodological and a very long approach to solving those problems. The problem is made substantially simpler, relatively speaking, by using Gauss's law, and that's what this chapter, much of it, is about. How to save a whole lot of time on your test-taking preparation and the actual test-taking itself, if you're taking a physics course on electricity and magnetism, etc. You want to have a good handle on how to use Gauss's law to your benefit. It's a very, very powerful tool and technique. So multiple examples are done in this chapter with the benefits of being able to read the symmetry of a particular problem and use this to your benefit. So several examples I'll work through in meticulous detail, and even though it may look a bit verbose and complicated, it's substantially simpler by this method than other methods if you're not using Gauss's law. And two additional terms are introduced here as we do some more example solving for electric fields. So here are some several places on Earth where the weather it's tremendously impacted by friction in the atmosphere. So here's one in Patagonia. This is one of my trips to the far south. This is in Patagonia, the foothills of the Great Andes Mountains. This is where it actually began. This is Tierra del Fuego National Park. And this is my flight into Ushuaia, and the southernmost city of the planet. And this is another picture taken in the extreme opposite part of the Earth, in the far north, well inside the Arctic Circle, in the middle of wintertime. Did some dog mushing over here. What do all these pictures have in common? Well, it's the extreme amount of snowfall, rainfall, thunder, and lightning that's associated with certain places. This is in Utah, and tremendous amounts of snowfall here as well. So any form of precipitation, what brings precipitation begins as moisture in the atmosphere, and the moisture in the atmosphere generates all of the weather conditions shown here in all these different places in the world that I've just quickly shown you. What comes out of this is that there are charged particles in the atmosphere caused by the friction of water molecules. Typically on a clear day, positive charges exist lower in the atmosphere, closer to the surface of the Earth, than negative charges. And this sets up an electric field that is directed towards the surface of the Earth from the sky. But during cloudy days, when thunderstorms are about to approach to bring the heavy rainfall and snow, as shown in all of these pictures I just showed you, the reverse is true. The electric field switches direction. Now, negative charges collect closer to the surface of the Earth, and positive charges are collected higher in the atmosphere. And this reverses the electric field direction within the atmosphere. Nevertheless, the electric field, when it builds up substantially, it has to break down, and it does so in the form of lightning strikes. So several examples are done to such an end to find out what the electric field and the total amount of charges within one cloud, for example, or surrounding one cloud, or what is the total amount of charge from the cloud through the atmosphere all the way down to the surface of the Earth where we live. That's probably of more importance to know because it affects everyday life. So several examples are done in this chapter to such an end, to be able to use Gauss's law to solve for electric field and charges contained. And to such an end, two new properties are developed here. The electric potential energy, which has to do with a system of charges. One charge references to another charge, and that's your system of charge. And it talks about the energy within the system. So you need multiple charges to have this make any sense. So electric potential energy, work is done by electric field on a charge, and that charge can now also do useful work in its own right. We can also define something else out of the electric potential energy if we took the electric potential energy of a system, of a charge in an electric field due to another charge. Now, if we look at the work done, the electric potential energy of a particular charge in a field, and we divided the electric potential energy by the magnitude of the charge itself, well, that gives us potential. The reader might know it as voltage. V typically represented for voltage, like a 9-volt battery or a 12-volt battery. So this is what voltage is all about. It's the ratio of the work done on a charge by electric field divided by the magnitude of the charge itself. And this is the definition of the voltage, right? Or the electric potential in more scientific terms. So several examples, as usual, for every chapter are done here, so the reader gets a good gauge on how to apply Gauss's law, electric potential, and the electric potential energy. I hope the reader finds it very useful. Once again, thank you for your time.